Okay, just a reminder to everybody. There is your remaining homeworks and things that are in there. These things are, we've already finished chapters 10 and 11, so that homework is due tomorrow, so don't forget about it. The chapter 13 and 14 homework, which is what we're working on right now, it's not due until after Thanksgiving. You've got a quiz that's gonna be due after Thanksgiving. And then at that point, we're just gonna have the final. So that's where we are with regard to class. So we are approaching finishing stuff up. Don't forget, you can follow things on the calendar. Due dates. So those are the things that are there. All right, so that's all working. I've lost my sharing screen. Interesting. Computer's doing weird things today, but that's all right. Totally fine. So now what we talked about on Tuesday, because today's Thursday, although this morning when I woke up, I couldn't tell if it was Thursday or Friday. Because I knew I had to be somewhere by 8 o'clock, and then I thought I was going to have to teach a class, but I didn't have to teach a class because it's Thursday. So it's that kind of a time in the semester. But we're focusing on what is, we were talking about static electricity. We talked about induced charges. We talked about how like charges repel, unlike charges attract. We talked about the electric field. But what we didn't start talking about was current. So we started talking about what makes a good conductor. And then we started saying that in order to get current, we could use that water analogy. So we're going to look at current a little bit more in depth. Electricity can bite. So you have to be safe around electricity. So when you guys are taking your safety class next semester, this is one of those things that we talk about in order to make sure that people are safe, because we don't want an electrical spark to start a kablooey. That's a bad thing. You don't want to do that. So electric current, if you think of a battery as a pump, a battery stores charge. So that charge is stored, but once I can complete a circuit, that charge can flow. And that's what's going to happen with our current. So you can play the Miss Frizzle game, and you can be standing by a section of current and you can watch the electrons move. Now what's happening really is you've got a series of cascades that are going on, but you can imagine that current can flow. So we use the water analogy. Water analogy works fairly well. And so we can make a circuit out of wire, a battery, and a light. Now you can think about how to put this together in order to get a circuit. And you can actually do this with a single wire. And that's how you would do that with a single wire. You're going to create a circuit where you have to have the battery connected with the little lamp. So that's exactly what happens with a flashlight. My flashlight really is doing that. I have to have a path that the electrons can flow, and I have to have my light inside that circuit. Now my light is also going to act as a resistor. These little incandescent lamps that you have in your old flashlights, they're little resistors. They're like 10-watt resistors. They're pretty small. But the thing about it is your current is going to go through the path of least resistance. So that's why we don't want to short things out. We don't want to be the human body that becomes the path of least resistance. That's something we definitely don't want to do. But we are going to create a circuit, and most of us know what that circuit looks like. So this one is going to give our battery, and that just goes through you guys do have these slides, and I uploaded the slides from Tuesday. So they are in your Blackboard. Those are absolutely uploaded. So I even think we talked a little bit about this because the slides that I had for electricity kind of combine the two things, but this textbook actually separates them out. So I wanted to make sure that we went through these things in a little more detail and used their pictures. So that's what we did. So we did talk about current. And current is going to be the number of charges per unit time. And the unit that we're going to use is an ampere. And this is our Miss Frizzle type idea. Now, this is reality. This is what Benjamin Franklin said. But what's actually moving are electrons. That's what's actually going to move. So we're going to push electrons that are out there. Okay. Maybe. There we go. So if I have an inductor or a heating coil, like what I have on my stove, or I have the little incandescent light bulb, and the reason we don't use incandescent light bulbs anymore is because they're energy hogs. They're energy hogs. And in fact, my house wouldn't have as many lights on in my circuits because I only have a 10 amp circuit, and some of the incandescent light bulbs eat up a lot of electricity. Now, you could still buy an incandescent light bulb. I actually have purchased them of recent vintage, but they're not sold as a light bulb. Well, they are sold as a light bulb. They're usually sold as heating lamps for lizards and plants. So if you want a heating lamp, those are traditional incandescents. But now, way back when President Bush kind of said we aren't going to do incandescent light bulbs anymore. And the real big reason is our grid can't handle everybody using incandescent light bulbs. That's one of the things that are there. So we talked about factors that impact resistance. The material, what's the materials made of, the diameter of the wire, and the temperature. All of those things are going to impact how much resistance is going to be there. So this one gives you a better look at the water analogy. My battery is my pump. My piping would be my lovely wire or my flow for the water. I get a constriction, that's where my resistor is, and I use my valve as my switch. So we can use that electric current analogy. We can use the water analogy for the electric current. We talked about Ohm's law. And that is going to be 1 ohm is equal to our current times resistance. It's going to be my ohm. So you get ohms in there. Ohm's law, you can have materials that are ohmic and you can have materials that aren't ohmic. And there is a nice linear relationship between resistance and current. So you can think about that. If the initial resistors were just lengths of wire, the longer the wire, the more voltage I've got to apply to get the same amount of current. And we talked about those pieces there. So you got Ohm's law again. And we can do those calculations. It's a simple calculation. V is equal to IR, or I is equal to V over R. So you can actually calculate your current based on your current based on your voltage and your resistance. And then you can also use your amp meter. So when we're measuring voltage, you're going to use a multimeter. And your multimeter would be like your battery tester. And you can actually read those battery testing items. So you get your Ohm's law there, but your amp meter has to be in the circuit because you have to have the circuit running through the amp meter. We talked about batteries. Summertime is what kills your battery. Wintertime is when you know it's dead. And that's because all real batteries have an internal resistance. So even though your battery is rated at 12 volts, you're probably only going to get 11.6 because of the internal resistance of the battery. Typically, if I have a 1.5 volt, which is going to be my AA's or my AAA's or my D batteries or my C batteries, those are all 1.5 volts. You're going to see like 1.49 because there's an internal resistance to the battery. And that's why we use this idea of an electromotive force. Because if you think about that water analogy, that water gives you that pump is going to give you a force to move things through. And even though we don't think about it that way, that voltage is a pump. We can use that as an electromotive force. So you'll see this E used as well as V. V is my electric potential. So you can work through those. So we can calculate the resistance of the battery. And we saw in my earlier slides from Tuesday, we saw that it's going to be different if I'm in series and parallel. But this one you can look at how you're going to go through and do the calculation. So this one's showing you your calculation. And again, it's a simple equation, so it's not too bad at all to get our voltage difference across. And again, our little batteries are about 1.5 volts, but you can see that you're going to read 1.2 volts because there's an internal resistance in the battery of 5 ohms. Although that's pretty high for our current battery that we use today. That would be a battery that's on its way to dying. If you get a 1.2 volt, and actually, if you guys have never done it, you'll find that that if you have devices that have more than one battery in them, like your lovely remote controllers, all those lovely things, you'll find that if you pop it out and you test your batteries, it's only one of your batteries that's gone dead. The other one still has a lot of juice in it. So if you're throwing away both of your batteries at the same time without testing them, I wouldn't recommend it. Now, if you're doing it to change out your fire detection systems and stuff like that, you probably want to put in both fresh batteries. But when you're doing like your remote controls, your mice, things that are common, having a nice battery tester or a nice multi-function tester out and around, it's really, really handy. You can get them at Harbor Freight for less than $5. Now, they won't measure current, okay? Well, no, the ones at Harbor Freight will measure current, but they won't measure capacitance. So your multimeter, you're gonna have a multimeter, and they run, and I'll tell you, they run from prices of cheapest one you can get is a 7-function 5. Actually, you can probably just get a regular battery tester, which is just one function, just doing voltage, to the 5 or the 7-function ones, which are about $5 at Harbor Freight, to the ones that I have purchased for the WIN program as we start working with other things that are $4,000 or $5,000. So multimeters and multi-testers they span the gamut. I purchased for my grandchildren, because I'm weird that way, I purchased for my grandchildren their own multi-testers, their multimeters, and I paid $35 for them because they were nice, digital, had 21 functions on them, those kinds of nice ones. They'll be able to have them in their toolbox for their entire lives. So that's worth purchasing and putting in your toolbox. The one that we use at home is an old analog one. I have an old time analog one, and we've had it for probably 40 years. And it's actually in my living room because we use it all the time. So it is definitely worth purchasing, having one around and throwing it in your toolbox. And you can always tell things are live, so those are fun things. So the resistance of our battery is in there, and that will cause us to have a drain. So we did talk about series and parallel circuits, but what I didn't do on Tuesday was show you how we would draw it in a chart that does this. So this is our symbol for a battery. A capacitor symbol looks very similar. A capacitor symbol is going to have both of the sides are going to be the same size if I have a capacitor. But this is a battery. Here's my battery. The longer side is the positive side. If we draw current through the system, even though we really know it's the electrons that are moving, which are negative, we draw current from the positive to the negative side. So we actually would draw our I to go up this way and through the switch, because Ben Franklin got it wrong. And we have to suffer for that. We totally have to suffer. But my resistor is going to use this jagged sawtooth type function. So you'll see these in your diagrams with that jagged sawtooth. That's what you will see. Now, the reason they've done it with a little circle around here is because that's going to give me a light bulb. So we usually have the little light bulbs are drawn that way. But I can have a bunch of resistors in series or in parallel, and I can draw my circuit. So this is a line diagram for a circuit. And as we add different pieces of electrical equipment, you're going to see different symbols added. You'll see inductors, which will be little curly Qs. You'll see the capacitors. You'll see diodes. You'll see sensors. You'll see anemometer or anemometers are things that measure wind speed. An amp meter is what will measure current. You'll see those in there, but you'll be able to see that piece. A lot of times you'll also see this might be given as a V for voltage. You'll see those because you guys may ultimately have to read line diagrams. And you may get line diagrams in boxes of electronic goods. What's always fun is to get a line diagram. Your electronic mouse is pretty simple. It's a really pretty simple little gizmo. And you'll get line diagrams in there. So here we've got a situation where we've got 3 resistors in series. And as we said on Tuesday, you're just going to add them up. And if we break one of them, if it's an incandescent light bulb and it burns out, that's going to act like a switch. It's not going to allow the current to flow. So we're not going to be able to have that current flow, and we want to have that continuous flow. And you'll still do your calculations for these systems the same way. You find an equivalence resistance. I can redraw this picture as having just one resistor here because it's going to act that way. And I can come up with an equivalent resistance so I can find the current in my entire loop just by going through and coming up with an equivalent resistance. Now, things get a little different as we discussed on Tuesday, that in this case, the current's going to come to point A and it's going to hit this spot and it has a choice. It can go, where's my mouse? It can go down this way, or it can go on, and it can go down this way, or it can go on, and it can go down this way. What we find is that the current is going to follow the path of least resistance. So if all 3 of these things have the same resistance, it doesn't really matter. But what we're also going to see is we will see that the light from each one of these is going to be dimmer, but it's gonna be the same as those across. Now, it's gonna do that, so when we get our parallel, we can still calculate the equivalent resistance of a parallel system. But we have to take into account that those may or may not be the same types of resistors, so my effective resistance is gonna be a little different. So we'll end up having that same situation, and this one gives you the same water analogy, that we had before. So we can look at that. So there's my parallel circuit. So when you see them drawn, you'll have these in series, and this is how a circuit is going to look in parallel on a schematic. You'll get that circuit in parallel in the schematic. Now, if I'm using my multimeter, you can have your voltmeter come in, and you can have your probes, and you can attach across. So this has got my voltmeter in parallel. So you can actually read your voltmeter, so you can actually see the voltage that's going across. And here is the one where I'm trying to measure current. It has to be in the line with the current. The current actually has to flow through your ammeter. Otherwise, it's not going to tell you nada. It won't tell you anything, and you aren't going to get the best. So, electric current is going to lead us to power, and that's where we finished on Tuesday. We got our power, and so if I'm thinking about the water analogy that we started with, we know we have gravitational potential energy. We know that it can flow through in here, and we can also have heat being given off. Now, heat was a non-conservative energy. We talked about that. Trying to capture all the heat is a little tough. Second law of thermodynamics is Mother Nature's not fair. Second law of thermodynamics says Mother Nature's not fair. I cannot transfer all of my energy and get work out of all of my energy. I'm going to lose some to the environment, and usually that means heat goes to the environment. So second law of thermodynamics is Mother Nature isn't fair. So now if we look at our battery system, that's exactly what's happening. And we know this. We totally know this. Our laptops get hot. Our cell phones get hot. As we're running current through our devices, they're going to get warm. And if it's getting warm, I'm losing some of that energy to heat, or in this case, to light. The heat and the light are going to be the same kind of thing, but I'm losing that. So I'm going to get a loss. And that loss is going to come in the idea of power. Power is energy per unit time, which you guys did before, right? You guys did the work power experiment. You guys ran up and down the stairs. You did that experiment. But my power was how fast I could do it. Now my power here is going to be related to current and energy. Now my electric bill, if I go and look at it, it's going to say kilowatt hours. So my watt is equal to my energy divided by the time. Joules divided by time is going to give me a watt, just like what we had mechanically. But if I take my time times my power, that's going to give me energy, and that's where our kilowatts come from. Kilowatts are going to be there. Now, the reason we go to AC versus DC is because we are going to lose power as we go through our transmission lines. We lose less power in an AC transmission line than we do in a DC transmission line. So if you want to see the calculation, here's our power. So we actually have multiple equations for power, which I did not show you before. So power can be our voltage times our current. Power can be our current squared times the resistance. And we do, we get our power in our system. So we end up losing power in real systems. But that power is what's going to help us drive and do the things that we want to do. So this is an example of an electrical grid system, which we didn't talk about on Tuesday. So we're going to do some sort of power generation. We can do a lot of power generation. There are all kinds of power generation. Historically, an OG&E down the way, Sooner plant is like the newest coal-fired power plant in the country. It's highly efficient, and for a coal-fired power plant, it's very clean. It's a coal-fired power plant. We've got power plants in the area that are natural gas fired. Don't have too many in our area that are diesel or fuel oil fired. If you go back to the East Coast, most of those fuel oil fired power sources are phasing out fairly quickly, but they're there for emergency backup. Some of us have emergency backup gasoline powered ones, your home generators. Some of those are backups or gasoline, some of them are diesel. But on the East Coast, you might have some old fuel oil ones that are still around as backup, but those are again going away. And what we're doing when we're at our power plant, whether your power plant is hydroelectric, wind, coal, natural gas, fuel oil, or we can use waste heat. That's what Continental Carbon is using the heat from their coke process to do what's known as cogeneration. So they're pulling off the waste heat of their process to do the same thing that somebody would be doing automatically by heating up your source. So what you're doing essentially is you're taking one of your fuel sources and you're heating up a bunch of water. You're going to take that water and you're going to convert it to steam. Steam is going to be used to push a turbine. And that turbine is going to either rotate wires or it's going to rotate a magnet depending on the configuration of your system. And it's going to generate your current. Now, we haven't talked about it in here, but you have your power plant. This is your power plant. It's going to go through some kind of transformer because we have to match what's on the grid in terms of its voltage and its frequency. Because I'm turning a turbine, it's going to have a frequency. Okay, it's going to be in a rotation, it's going to have angular velocity because I'm in a rotation, and I have to match my frequency and my voltage to put it onto our grid. And if you guys have not been south of here recently, you're seeing a lot of high voltage power poles that are going in. In fact, I was watching one of the guys, I was coming up from Stillwater on Tuesday. There's a new one that's just south of 412 that the guys are out there. They're going to be running the high power cables before too much longer, that they're putting in those poles to give us more electric grid generation. So we get we're going to have, this would be what we call a step up transformer. And you'll see these at the refinery because all the refineries are going to have a power station. They're going to be pulling electricity off the grid. And if they have cogeneration, they're going to be putting electricity back on the grid. You can even do that with solar cells, wind turbines, although in the state of Oklahoma, we don't do as much as the people in California do, or various other things that you can have at your house could be an actual electric generation system. If you have wind or solar at your house, those you can actually put on. So this, if I'm doing wind is a turbine, the only power generation right now, well, there's other power generation. You can have solar cells, that's another way to generate electricity. That's going direct from solar radiation to an electrical current. Geothermal is another way that you can do power generation. Then you can do some weird ones. You can actually use changes in frequency to generate electricity, because if you have a changing magnetic field, you can generate a current, right? You have to have a changing magnetic field. There's a lot of ways you can get that changing magnetic field. The most common way is to either spin the magnet or spin wire in a magnetic field, which is what we do with a turbine. But if you follow some interesting power generation ideas, they have the ones that are done with waves. You've got a buoy that's bobbing up and down that's using wave action. That could give me a changing magnetic field. Okay, or I can be moving my wire through a changing magnetic field. So that's an interesting way. There's another one they're testing in various places where they're using the vibrations in walkways. It's people walking across walkways. That gives you a changing magnetic field, and you can generate current that way. Those are some of the more interesting ones. Not going to generate a whole lot for our needs, but it will generate some. But we can get it onto our power grid. If we're going long distances, we want high voltage because we have lower power losses. We have lower power losses. And then as we get to our local areas, usually you'll see a transfer station near a community, as you're going to be pulling off of the main big high voltage ones. We're going to have a step down transformer, and we'll get that step down. Typically, you're going to be in 3 phases. You'll have 3 phases in there. And then you get your local distribution lines, and then your individual house transformers that you have out there. And you even may have a transformer at your home. And you may even have some built into your boxes that you bring in your electricity. But that is our electrical grid system. Now, our infrastructure from a lot of our electric grid can be old. And again, we're using a lot more electricity, so we have a lot more things that are going on. So we see kilowatts, that's 1,000 watts. Ours, let's see, is 3,600 joules. So 1 kilowatt hour is 3.6 million joules. And if you've ever looked at your electric bill, think about that in terms of energy and your energy usage. So if I had an old incandescent light bulb, an old 60-watt light bulb that I was running for an hour, 60 times 60 is 300, or it's 3,600. That's 3,600 watts of 3,600 watts, 3,600 joules to run a 60-watt light bulb for 1 hour. Your LEDs, they're like 4 watts, which is why LEDs are so much more energy efficient. And you can reduce your electric bill drastically just by converting over to LEDs. I used to do that calculation and show that calculation. I have it in several places on my YouTube channel and see the calculation. I was a late adopter of LEDs, terribly late adopter, even though I knew the energy efficiency and the energy savings of them. It wasn't until fairly recently that LED lights didn't hurt your eyes when you were trying to read off a white paper. And so it was an eye situation, not an energy situation that had me not adopt the light bulbs. But basically you can run one LED for its entire lifetime, which is like 15 years, for less than $100, and it'll cost you almost $1,000 for the same time using incandescent light bulbs. So, I mean, that's what we were dealing with. So alternating current, that's what we work with. We work with that because we don't want to use power losses. In the United States, we're at 60 hertz. Europe's different. The United States, 60. That's what we do. And basically what happens is your current's going to look like this. We actually use something that we call our peak, and then we use our effective current. And our effective current is also the root mean square. That's where we get that lovely number. And that's what we utilize for our sine wave, and that's what we go back and forth and use our alternating current. And that helps with our power generation and efficiency in our power generation. So alternating current is what we typically do. DC, you can generate DC, but DC is not near as efficient over long distances. And so we can get those things there. So our 60-watt, our historic 60-watt light bulb is in there. We run to our main lines. We have circuit breakers. Circuit breakers are so that we don't overload our lines or overheat, but we end up doing a lot of things. We do use the 220 volt line. We have 120 volts AC, but we use that 220 for bigger pieces of equipment, pumps. You got big pumps, bigger air conditioning units. Your air conditioning unit is probably a 220. Furnace is if you've got an electric furnace, it's probably a 220. Your dryers are 220. Your stoves are 220. That if you're dealing with electric current. Questions? I gave you the basic thumbnail overview. Yeah.
This is kind of a tough question, but you hear of the transformer blowing all the time. Is that because it's overloaded with the high voltage?
Usually what's happening is they're shorting out. You've had something that's crossed it. So I guess Pawhuska had a power outage not terribly long ago, and they showed the culprit. The culprit was a raccoon, and if you see the tops, if you see the two tops of the item, the raccoon touched both sides at the same time, he became a crispy critter. He became a crispy critter. Usually what's happening when the transformers blow is somebody's done a short, and that short has caused, and it could be a short due to a wire. Usually what's happening around here, you might get a bolt of lightning that comes in that's gonna just overpower it and go from that. And then around, like you go back here behind Harold, the Purple Aquarium building. You go behind Harold, you'll see that stack of transformers, and a tree branch can come across and short it out, and that's what's going to cause your. And they're filled with an oil. They're filled with a transformer oil, so they are flammable. So even though those oils can take very high temperatures, but when you give it a zot like that, it's going to blow. That's usually what's happening with the transformers. Is that something has crossed it, and whether that's a wire, and that's usually what happens. The wind is blowing loose a wire and it's caused it, or you've had an electric or a lightning strike that will have caused it, or a raccoon, or a snake. Snakes are always fun because most of the time, if a snake goes across, you're only finding one end of it. And it's pretty, because they get vaporized. They're like an interesting little wire and they get vaporized. And I have seen the remnants of a snake. It's not, you find either the head or the tail. You don't find the in between. They become poof. They go poof and, yeah. And I'll tell you guys, it took me, when I first started here at NSC, which has been, it'll be 11 years in January. I was still saying bad things when you'd see the lights flicker. And I hadn't been inside a refinery. Oh, I'd been inside the refinery, but I hadn't been responsible for a refinery when the lights flickered in 20 years. So it took me over 20 years not to say bad things when you saw power bumps. Took me 20 years not to have nice, pretty, colorful language when the power started flickering. Because that's a bad day. The Woods Cross refinery, we came down. We lost a phase. One of the things about the 220 and is you actually have 3 phases for high power equipment. You have the capacitors will help get things even on the way up. Resistors are real time. Inductors help you not have the changes in the system. And so all your big equipment, all your big pumps, all your big compressors, anything that has large rotating equipment is going to be in 3 phase. And if you lose just one phase, all that gets to be rewired. All that gets to be redone. And when the refinery comes down because you lost a phase, people are not happy campers. They say very bad things. It's a bad day. We don't like those days. Yeah, so brownouts kill a refinery. And somebody says, well, can you put an uninterruptible power supply on a refinery? No, they don't work like that. You don't have one big enough. So yeah, it took me a long time not to say nice, colorful words. Other questions? All righty, folks. We're gonna start magnetism. We're gonna play with magnets next week.